An observer at rest relative to Earth observes two spaceships. Each spaceship is moving with a speed of 0.85 c but in opposite directions. The observer measures the rate of increase of distance between the spaceships to be 1.7 c. Outline whether this observation contravenes the theory of special relativity. Theory suggests that no object can travel faster than light. The 1.7 c is not the speed of physical object, so is not in violation of the theory. The next question. Determine according to an observer in one of the spaceships the speed of the other spaceship. So this situation looks like this. There is the Earth reference frame S, and there are two rockets. One is moving to the left with speed 0.85 c and another is moving to the right with 0.85 c, and we need speed of the rocket relative to one of the rockets, and let's find relative to this rocket. So we choose this rocket to be moving reference frame as primed, and it is moving to the left, so we need speed of this rocket relative to this rocket. So it's in moving reference frame, and using a formula. What formula? U primed is U minus V divided by 1 minus UV over c squared. When you use this formula, plus or minus, it's essential, it's very important. And it means you should take into account velocities actually. So U prime, it's what is the velocity of this rocket in this reference frame. What is U? U is speed of this object, sorry, not speed, velocity of this object in this Earth reference frame, or it just plus, because direction to the right is chosen to be positive, plus 0.85 c minus, what is V? It's a velocity of moving reference frame, it's to the left, so it's minus, so it's minus negative 0.85 c divided by 1 minus 0.85 c multiplied by V, which is negative 0.85 c, so it will be 1 plus and product divided by c squared, and it becomes plus 0.99 c to two significant figures. Or we can choose this rocket as moving reference frame and find the velocity of this rocket relative to this rocket, and it will be like this. So as primed, and it is moving to the right, and we need this velocity in moving reference frame. So again, we need in moving reference frame, so we use same formula. U primed is U minus V 1 minus UV over c squared. And what is U? It's this, but it's to the left, so it's negative 0.85 c minus V, it's positive 1 minus U, it's negative 0.85 c times V is positive. And you can see that we get absolutely the same by magnitude. Denominator is the same, 1 plus, and you can see that here it's 1.7, but here it's negative 1.7, and finally we get negative 0.99 c. Minus just indicates that direction is to the left, so velocity of this rocket relative to this rocket is to the left, because positive direction is chosen to be to the right. And here it means that direction of this rocket relative to this rocket is to the right. The next, The observer on Earth in A watches one spaceship as it travels to a distant star at speed of 0.85 c. According to the observers on the spaceship, this journey takes 8.0 years. Calculate according to the observer on Earth the time taken for the journey to the star. Time interval in moving reference frame is proper time because measurements are made in the same point, at the same place. For example, it's the origin of this coordinate system somewhere at the same place in the spaceship. And the observer on the Earth will measure time to be dilated. It will watch slow motion. And it becomes delta t. Earth is not moving, not primed reference frame. Gamma delta t primed, where delta t primed it's this value, and gamma is a factor which is 1 over root 1 minus v squared over c squared. It's always greater or equal than 1, and it becomes 1 over root 1 minus 0.85 squared over c squared over c squared, so just 1 minus 0.85 squared, and it's 1.89 to 3 significant figures, and finally it becomes 1.89 times 8 years, and it becomes 15 years to 2 significant figures. Or you may use this formula, delta t not prime, delta, we need delta t is gamma delta t prime plus v delta x primed c squared, and delta x primed is 0 because two measurements are made in the same coordinate in the spaceship, and primed is moving reference frame, and you can see that you get absolutely the same formula. The next, outline whether the time interval measured by the observer on Earth is a proper time interval. No, it's not proper time interval because measurements, or because the time is not measured at the same place between two events. Calculate according to the observer on Earth the distance from Earth to the star. Distance. What is distance? Distance is speed times time, and in Earth reference frame, speed is 0.85 c, and in the Earth reference frame, time required is 15 years. 15 years. And it becomes 12.8 or 13 years, not actually years, because if c at speed of light multiplied by year, it becomes light year. It becomes light years, 13 light years. And actually distance measured in the Earth reference frame, it will be proper length, because distance is measured where it is stationary. It's proper length, and distance measured in moving reference frame, this distance will be contracted. It's called length contraction. So if you use time in moving reference frame 8 instead of 15, you will calculate distance according to moving reference frame. So you must multiply it by 1.80 by gamma 89 to get larger length, which it will be proper length according to the observer on the Earth. Or you use directly time in the Earth reference frame and speed of the rocket. But notice that years, and together with C we get answer to be in light years. Light years, it means that it's about distance. The next, the observers in the spaceship send a message to Earth halfway through the journey. Determine how long it takes the message to arrive at Earth according to the observers on the spaceship. So we need in moving reference frame. So halfway in the Earth reference frame, it's 13/2, but it's 12.8 to be more accurate, and let's choose it to be 6.4, but you may take 6.5, it doesn't matter. Light years in some x coordinate, and at this moment of time it's a rocket's reference frame. A signal is sent. It's a light actually, so it travels with speed of light. And we need what? Time in moving reference frame. So we need delta t prime. And you may remember and don't get confused when we use just length contraction or time dilation instead of these long formulas. What formulas? This formula delta t prime is gamma delta t minus v delta x over delta x over c squared. It's actually the same, but for previous examples, or when we use just time dilation or length contraction, it's just because this is equal to 0, and when there is some additional travel, for example, like this signal is sent or something additionally is moving, it's usually a signal which is light. You should use this formula, not just this or length contraction, that length is length divided by gamma, something like that. And we need substitute correctly. So time interval in moving reference frame becomes gamma. What is gamma? 1.89. And time to travel in the Earth reference frame. And in the Earth reference frame is 6. We should move what distance? This distance with speed c. So it becomes 6.4 light years divided by c. Minus, what is v? V it's velocity of moving reference frame, and this rocket is moving to the right with speed 0.85 c, so it becomes plus 0.85 c. Delta x, it's interval in coordinates traveled by light, but you can see that it is moving to the left, so final coordinate is 0, initial 6.4, so change in coordinates it's negative, so it becomes plus, let's write negative 6.4 light years divided by c squared. And light, you remember that light years it's c multiplied by years, so we can divide by C, so we get time to be in years. And also here one C cancels and another C here, so you get just what, 6.4 plus 185 times 6.4, and in it becomes in years, and 1.85, and you can see, you can factor out 6.4, so finally it becomes 1.85 times 6.4 and times 1.89, so it's 22 years to two significant figures. So it's approximately 22 years to two significant figures. And that's all for this question.